Yeah. Just go ahead and, make it, and you go ahead and go. I'll approve it in a minute. So first compound we're looking at here, and we're going to write whether these are soluble or insoluble. And just to practice, I also want to put AQ or S after them as well to practice doing that. The first one says AlCl3. So always start with rule number 1 until you get familiar with them. Once you get familiar, you might go in a different order. But rule number 1 and 2 are the most important rules, so we always start with those. Rule number 1, all compounds containing group 1 metals and the ammonium ion are soluble. Does aluminum chloride have a group 1 metal in it? Nope. So you go to rule number 2. All nitrates, perchlorates, chlorates, and acetates are soluble. Does that apply to AlCl3? Nope. So then you go to rule number 3. All chlorides, bromides, and iodides are soluble. Does that apply to this question? Yeah, because this is a chloride. Since this is aluminum chloride, that means this compound is going to be soluble. So I'm going to write soluble on the left-hand side. That way I can practice on the right-hand side, putting AQ, aqueous, because that's what you'll be doing when you get to the back of this, is putting AQ or S after the compounds. So yeah, it's going to be soluble because it's a chloride. Is it one of those exceptions on rule number 3? No. That's how I know for sure. Once I get to a rule that describes it, I can move on to the next question. All right, let's do the same thing in Mg3PO42. Is Mg a group 1 metal? Nope. So rule 1 doesn't apply. Rule 2, is there a nitrate or a chlorate or acetate? Nope. So you go to rule 3. Is there a chloride, bromide, or iodide? Nope, not in this one. 4 is sulfate. Is there a sulfate here? Nope. All right, rule number 5 is OH and O. Is there hydroxide or oxide here? Nope. So finally, the very last one is about phosphates. Rule number 6 mentions phosphates, right? What does it say about things that contain phosphate? They're insoluble. So remember, those last 2 rules, 5 and 6, are about things that are insoluble. Since it's insoluble, after it, I'm going to put S for solid. I hate the fact that soluble and solid both start with the same 3 letters. That means if that were to form in a reaction, that would be my precipitate, and it would sink to the bottom. Okay, the third example is magnesium nitrate. Same idea. We already decided it's not a group 1 metal. Magnesium is not a group 1 metal. So then the second one is about nitrates. Rule number 2, all nitrates are what? Soluble. So I'm going to put soluble. And then I'm going to put AQ after it. Things that are soluble, you write AQ. That means they would dissolve in water. So you take a little bit of time to do the next 8. And as you do these, you'll get a lot more familiar with your solubility rules, which will help you be quicker when we get to the more complicated stuff on the back. All right. What did you get for letter A, which is barium nitrate? Luke, letter A. You got it. It's soluble, so I'm just going to put AQ after the ones that are soluble. I'll write it on the first couple as an example. But next one, letter B, ZnS, zinc sulfide. That's sulfide, IDE. It's just sulfur there. Riley, what did you get for letter B?
I got insoluble.
Yes. Good job. So that's going to be a solid. That would not dissolve in water. So insoluble. From now on, I'm just going to put AQ or S. Camden, what about letter C? What'd you get? Okay, let's look at this one. This one, it starts off with NH4. As soon as you see NH4, the polyatomic ion, I want you to look at rule number 1. And what does it say about anything that contains NH4? Soluble, you got it. And as you do more and more of these, you get familiar with like that first rule. So you can, those will jump out to you eventually, but they're brand new right now. Next up, letter D, Fe2O3. Darian, what'd you get for that one? Letter D for Darian. Insoluble, good job. That's considered an oxide. So that one's going to be insoluble. Letter E, PbCl2. What'd you get for that one, Logan? Insoluble is the answer again. All chlorides are soluble except those containing lead and mercury and some other metal there. I can't remember the other one right now. Letter F. Lily, what'd you get for F? Soluble, you got it. I'll put AQ because it's soluble there. As soon as you see sodium, and you know sodium's in group 1 on the periodic table, there's your answer. It's soluble. Letter G. Callie, what'd you put for letter G? Good answer. That is the correct answer. So everybody check yours on these as we go through them as well. That one's going to be insoluble, so it's a solid. Chromate is like the very last rule at the bottom there. That CrO4 is in the very last rule. Rule number 6. And then last one here, FeBr2. Hallie, what did you put for this one? Good job. AQ. Bromides are soluble. All chlorides, bromides, and iodides are soluble except for a few, but iron's not the exception. Yeah.
I have a question about G. Okay, so how come I got soluble for G?
Okay.
And I'm just confused because wouldn't it be an oxide if oxygen?
Oh, you saw the other one?
Because isn't,
I know why you're confused because chromate is a polyatomic ion that we don't see much, so we haven't seen it a whole lot, but CrO4 is a polyatomic ion, and so when you get down to rule number 6, it's called chromate. Rule number 6 says all compounds containing phosphate, sulfide, blah, 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 and chromate are insoluble, so that's the reason we have to go with insoluble for that one. Yeah, you bring up a good point. When it says oxides on rule number 5, that would be if it's just oxygen. So if it were like BaO, that's considered the oxide, and that one would be therefore soluble if that were the question. The chromium messes that up, so it's not just barium oxide. Yeah, you're welcome. We will see that one, CrO4, maybe on something. So, all right. So that's how we use the solubility rules. Now let's get into the actual reactions that we're going to be talking about today. So back on the notes page, let's look at the bottom half of some examples, and then we're going to practice writing some reactions. So double replacement reactions are actually pretty easy to predict whether they occur or not once you're good with the solubility rules. The very first thing that you do when you get a question like this, you would have to switch your partners. Like in this first one, the Na and the I get together, so there's NaI, and then also the K and the Cl get together, and there's KCl. Well, you would look up each one of them for the solubility rules, and you would find out that both of these are soluble because they both contain group 1 metals. When they're both soluble, nothing really happens. You're actually just mixing one kind of salt water with another kind of salt water, and you mix them together, and you get a big beaker or test tube full of 2 kinds of salt water mixed together. But nothing actually happens. Because they're both aqueous, a precipitate does not form. So you just write no reaction, and you get to move on to the next question. You don't have to worry about balancing it or anything when it's no reaction. But the second bullet point says, if at least one product is insoluble, then a reaction occurs. Therefore, we have to write the reaction and balance the equation. So that's when we have to do some work that might take up to maybe 5 minutes on a question, where you really have to put together your charges of your ions and then balance the overall reaction. So on this second one, testing it out, Ag and Cl get together, and then also the nitrate and the sodium get together. When you look up your solubility rules for these things, the sodium and the chloride, it turns out, is insoluble. The thing that's insoluble is the solid precipitate. That's what the S means here. That's the solid precipitate. That is actually what reacted S refers to the solid precipitate that forms. That's what actually reacted. The thing that's aqueous, that tells us that these are going to be the spectator ions that didn't actually react. They didn't form a precipitate. So just like at a ball game, maybe there are spectators. They're not really playing in the game, but they're still there in the background. They're the spectator ions. There's actually two of them there. In this case, the sodium and the nitrate are the spectator ions. The spectator ions, they remain in solution. So sodium and nitrate, I'm going to put a comma between them, or the word and could go between them because they didn't really bond. They didn't react with each other. In the example on the board, all right, in the solution up here on the top of this test tube, this is salt water. The salt, the sodium and the chloride, they didn't really bond and form a solid precipitate, so they're just floating around in solution as ions. But they didn't really react. They're the spectators. The calcium and the carbonate really reacted when it formed that precipitate. So flip your sheet over and let's take a look at some examples of how to do these. To predict a double replacement reaction, the first thing you want to do is switch the partners of your reactants. So just take the insides together and the outside ions together. When you put the inside ones together, be sure you put your positive ion first, like calcium came before carbonate in my right-hand side over there. Check the solubility of the products. So then I would have looked up sodium and chloride, and I would have seen group 1 metal in sodium, so I would have said AQ for that one. I would have checked all my solubility rules for this one and found that the carbonate meant it was going to be the solid precipitate. If both products are soluble, you put no reaction because nothing forms a precipitate, nothing happens. But if one of the products is a solid, that means a reaction occurs, and you have to balance the individual charges of the compound, the other compound as well, and the last step is to balance the overall reaction. Kind of like we did with the single replacement. We had to think about charges before we could balance with coefficients. Okay, so let's try this example that we see here. This is sodium bromide plus calcium chloride. My very first thing to do is find out whether or not a reaction occurs. So I'm going to put together the sodium and the chloride. I'm going to leave some space for all the AQ stuff and all that. And then I'm also going to put together the other pair. Should I say BRCA? How does that look? Is that okay? Oh, Ca comes first because it's the metal. It's the positive charged ion. So for those insides, it's always the second one that becomes first on the right-hand side. Now let's look up our solubility rules for each of these. All right, look up NaCl. NaCl, check your solubility rules. Rule number 1. All group 1 metals are soluble. Does that affect NaCl? Is Na a group 1 metal? Yeah. Yep, that means this is going to be AQ. And hopefully by now we know sodium chloride is soluble. It's salt water. Sodium chloride dissolved in water. Let's do the same thing with CaBr. Rule number 1, group 1 metal. Is Ca a group 1 metal? Nope, so go on to rule number 2. Nitrate, chlorate, acetate, any of those here? Nope. So you move on to the next one. Rule number 3. Does rule number 3 apply to CaBr? Yeah, because it's a bromide. All bromides are soluble. So if it's soluble, what do I write after it? AQ. Are both products AQ? Yep. That means nothing formed a precipitate. Nothing actually happened. You just mixed together two kinds of salt water, but they didn't really react. If it's no reaction, don't worry about positives, negatives, balancing. You're done. You move on to the next question. You think the next one example is going to have a reaction? Yeah, because we want to see one of each, huh? So the next one's going to take a little longer. Does anybody need more time before I scroll? All right, this next one, FeCl2 plus LiOH. There's our reactants. Let's put together our products. It's the products that you always worry about as far as dissolved in water or not. The reactants are always going to be aqueous. You don't have to check your reactant side. So we've got Fe and then OH, which is hydroxide. So I'm going to say blank FeOH. Plus, what would my other potential product be here? Good, Li and Cl. It's just Li and Cl, okay? The 2 does not follow chloride to the other side because it's not pure chlorine. It's just chlorine as part of a compound. So don't let that little 2 after the Cl go to the other side unless it's part of a polyatomic identity like in carbonate. The 3 did have to go to the other side. Now let's use our solubility rules. Look up FeOH. Use your solubility rules to predict whether it's going to be dissolved in water, soluble, or insoluble, solid. I heard somebody say insoluble. What rule did you use for that? Yeah, if you look at rule number 5, all hydroxides are insoluble except for a few. As soon as you make something solid, you know you have to complete this reaction, which is a pain. But it's what we got to do. And then LiCl, is LiCl going to be soluble or insoluble? Yeah, it's soluble because it's a group 1 metal. Lithium is a group 1 metal. So it's definitely soluble. Okay, any questions so far? We've still got work to do, but at this point, does anybody have any questions? Once we know a reaction occurs, the next thing we have to do is make sure that our individual compounds have charges that add up to 0. So we may have to use some subscripts to do that. So for example, iron, in this case, iron has a positive 2 charge. I know that because the left-hand side has FeCl2. And then hydroxide is a polyatomic ion. What is the charge of the polyatomic ion hydroxide? Yeah, good. It's -1. I could use my pink list to find that if I needed it. So if hydroxide is -1 and iron is +2, how many hydroxides do I need to balance out the iron? 2. So I need another one, so I've got to use parentheses and a little 2 there. I need 2 hydroxides for every iron. Then I go to my next compound in blue. The charge of lithium, what's the charge of lithium as an ion? +1, it's in group 1. Chloride's still -1. Does that add up to 0? Yeah. So I focused on individual compounds first. Then I need to balance the whole thing. Most of us maybe are doing that in our head now, which is great, but if not, you could just, maybe on scrap paper, you could list your ions if you wanted to or needed to. That's this thing. 1, 2, 1, 1, 1, 1, 1, 2. In the end, we've done a lot of balancing. I'll get this thing balanced like so. And I'm almost done. I have to do the spectator ions part now. But the most important things I've just done. Predicted the products, found out one of them is going to be insoluble. Once I did that, I focused on charges of individual compounds first. And then the last thing I did was to put coefficients in. Now, spectator ions. To identify your spectators, everybody, it seems harder than it really is, I think, for us at first. You just find your aqueous product, and then you divide it up into its ions. Lithium has a positive 1 charge, and chlorine has a negative 1 charge. So just Cl minus or Cl minus 1. You don't have to put the 1 there. So your spectator ions are your aqueous product. Break it up into ions. So you separate them from one another because they're floating around in the solution up above the solid product. All right, let's start the assignment together, and then you'll keep going on your own after that. There's an example at the top of the assignment. I wanted us to have one to do together, actually on the assignment itself. Where is it here? Okay, it says predict the products of the following double replacement reactions. If a reaction does not occur, you just write NR. If a reaction does occur, we have to write the formulas for everything and then balance the overall reactions. We're going to get a lot of practice here. All right, so let's put together our potential products in the example. It says silver nitrate plus potassium phosphate. Well, let's put together the silver and the phosphate. I'm going to do it in words first, and then if there's no reaction, I don't have to do anything else. But if there's a reaction, then I will have to write them all as symbols. There's the silver phosphate. And then, is it going to be nitrate potassium or something else? Oh, potassium nitrate. Potassium comes first. It's supposed to be nitrate. I'm off the screen. Check your solubility rules. Silver phosphate. And guys, listen, one more time, I'm going to say it again. The reactants are definitely aqueous. You don't have to worry about looking them up. It's the products you have to look up. So silver phosphate, the first product we're going to look up. Go through all your rules. It's rule number 6 we're going to focus on here. What does rule number 6 say about things that include phosphate? Insoluble. That means it's a solid. That means I'm going to have to go through with this whole reaction. The next one, potassium nitrate. As soon as I see potassium, potassium's a group 1 metal. So I know that says AQ after it. Kind of sloppy there. That means I need to write a reaction here. So here we go. I'm going to have silver nitrate. Reactants are definitely AQ. Potassium phosphate next. K. Turns out it's K3PO4 because phosphate's got a negative 3 charge. Potassium has a positive 1 charge. These worksheets are set up. We just assume the reactants are aqueous. Now on this side, we got to put these together. Silver phosphate. It's going to be Ag and PO4. I just found out that's my solid. Plus potassium is K. Nitrate's NO3. So I've got those put together, and then I need to think about charges here. Individual compounds. On the left side, silver's +1, nitrate's -1. That's good. Potassium was +1, phosphate was -3, I did it while I was writing it. I should have probably gone in the order that I talked about it. I needed 3 potassiums for every phosphate. That's why it's K3PO4. Other side, silver is always +1. It's on that blue sheet. That's how I know that. Phosphate's still -3. So if silver is +1 and phosphate's -3, Luke, put that away, please. How many silvers do I need for every phosphate? 3. So I'm going to put a little 3 after Ag. And then finally, potassium's +1, nitrate's still -1. What am I going to have here? Any subscripts needed? Nope. The 3 is part of nitrate's identity, so I don't need anything else there, except a little AQ after it. What's the very last step for these chemical reactions? Balance the whole thing with coefficients. I'll do that in blue. It's the last step here. I've got 1 silver on the left, but I've got 3 silvers on the right. How can I balance the silvers? Put a big 3 here. Okay, now I've got 3 nitrates on the left and 3 potassiums on the left. So how can I balance the Ks and the NO3s? A big, you got it. Good job, Riley. 3 in front of potassium nitrate. So that was my very final step, was to balance with coefficients. All right, so when you have a solid product, you got to do a lot of work because you have to balance the charges on each reactant and product here, and then you balance the whole thing with coefficients. When both of the products are aqueous, you just put no reaction and you get to go to the next one. So on a few of these, you don't have to do all this work, but on a lot of them, you're going to have to go through and deal with that. Does anybody have any questions at this point?